So we have this definition of similarity, right? Matrices are similar when when you can write one of them as P inverse times the second one times P. And the idea here is that these matrices represent the same linear transformation, but just in different bases. So one thing we can do with this idea of similarity is go looking for the nicest kind of linear transformation. So what is the nicest kind of linear transformation? Well, that's kind of a vague term, but what I have in mind in particular is if you have a linear transformation that just has non-zero entries only on the diagonal, like this, so an n by n matrix that has non-zero entries only on the diagonal, this is especially nice because what this linear transformation does is it takes your standard basis, right? So here I'm drawing it as if we're in R3, but it takes your standard basis and it just sort of stretches them by different amounts. It stretches each standard basis vector by different amounts. Right? The first basis vector gets scaled by the scalar in the 1, 1 position. The second basis vector gets scaled by the scalar in the 2, 2 position, and so on. So this is a really nice kind of linear transformation because, geometrically it's so clear what's going on. Also, another really nice thing about this kind of linear transformation, or this matrix, is that the eigenvalues of this matrix are just the entries on the diagonal, and the eigenvectors are the standard basis vectors. So a diagonal matrix is really, really nice. And that means that any linear transformation that looks like this is diagonal. Well, hold a phone. A linear transformation, right, could have different matrices depending on the basis, right? Coming up with a diagonal matrix really depended on it having this action on the standard basis vectors. So what if it does the same sort of thing to a base? What if a linear transformation does the same sort of thing to a basis, just stretching each basis vector, but it doesn't do it to the standard basis? What if it does it to some other basis? Well, in that case, your matrix relative to the standard basis wouldn't be diagonal. But if you wrote the matrix relative to the nice basis for that linear transformation, then it would be diagonal. The matrix relative to that basis would be diagonal. What that means is being diagonal isn't really a property of linear transformations, but being similar to a diagonal matrix is a property of linear transformations. So we'll say that a matrix is similar to when a matrix is similar to a diagonal matrix, we'll say that the matrix A is diagonalizable. So when is it that a matrix is diagonalizable? Well, if it is diagonalizable, then we can write, so if A is similar to a diagonal matrix, that means it has to look like P inverse times the diagonal matrix D times P. Okay, and actually I want to write this one the other way. I want to write this as P dP inverse. Okay, and let's write the columns of P as, say, V1 through Vn. Okay, also, let's write the entries of D as just D1 down to Dn. Okay, so yes, so what happens if we take one of these vectors and multiply it by A? Okay, so it could be any one of these, so I'll write Vi. Well, A, right, A is similar to D, so A is P times D times P inverse times the vector Vi. What is P inverse times Vi? Well, right, P times Ei, what is P times Ei? Well, when you multiply a matrix times a standard basis vector, it just picks off the corresponding column of that matrix, right? So P times Ei is Vi, since Vi is the ith column of the matrix P. And so the inverse matrix does the reverse. When you multiply the inverse matrix times VI, you get EI. So this is P times D times EI. And then what happens when we multiply EI times this diagonal matrix D? Well, if you imagine multiplying this matrix by a vector full of zeros, but with a 1 just in a single position, all that happens is, right, you get zeros everywhere when you do this matrix product, except when this 1 hits the diagonal entry in the corresponding entry. But what entry is that? Well, it's the same entry as wherever this 1 is. This is a long way of saying that D times EI is just DI times EI, right? Try it out with an example if you aren't seeing it. Okay, but then, well, look, now DI, that's a scalar, so we can move that DI over to here, DI times P times EI. And what's P times EI? Well, P times EI, that's VI. And look, we had a vector VI, we multiplied it by A, and what we got is a scalar times that same vector. Okay, so that means that VI is an eigenvector for the matrix A. In particular, the eigenvector associated to the eigenvalue that is this diagonal entry, right? It turns out these diagonal entries are the eigenvalues for the matrix. Eigenvalues for A. Okay, so, right, we assumed that this matrix was diagonalizable, and what we found is that the columns of this matrix P from our similarity relationship are eigenvectors for A. Okay, well, every matrix has some eigenvectors. What's special about these eigenvectors? What's special about these eigenvectors is they formed the columns for an invertible matrix. That means that the columns of this matrix have to be a basis for Rn. And that means that the eigenvectors for A are a basis for Rn. Okay, so we assumed that a matrix was diagonalizable, and what we got is a basis for Rn made entirely of eigenvectors for A. That kind of makes you wonder, does this work backwards? If you have a basis of eigenvectors, is the matrix A diagonalizable? Well, let's check. So suppose that A has linearly independent eigenvectors v1 through vn. Okay. By assuming these eigenvectors are linearly independent, since there are n of them, that means that these eigenvectors form a basis for Rn. And also, let's assume that the corresponding eigenvalues are lambda 1 through lambda n. Now, some of these eigenvalues might actually be repeated, right? It's possible to have two linearly independent eigenvectors have the same eigenvalue. Okay, so this is our setup. This is what we get just from assuming that we have a basis of eigenvectors. So now we want to know, is A diagonalizable? Is it similar to a diagonal matrix? Well, you know, our proving this the other way actually gives us a hint on what to do. If A is similar to a diagonal matrix, the diagonal matrix probably ought to have eigenvalues down the diagonal, and this matrix P probably ought to be made up out of a basis of eigenvectors. So let's check. Let's guess that the matrix that we want, or the diagonalizing, or the way to diagonalize A is to, so I guess, let's say pack the eigenvectors into a matrix P. We know P will be invertible because these vectors v1 through vn form a basis for Rn. Let's let D be a matrix, a diagonal matrix with the eigenvalues down the diagonal. And then let's form a matrix B, which is P, D, P inverse. Now our hope, what we're secretly hoping here, is that B is actually A, right? Because B is clearly diagonalizable because we've written it as similar to a diagonal matrix. So if we can show that B is actually the same thing as the same matrix as A, then we're done, because we will know that A is diagonalizable. Okay, well, how can we check if two matrices are equal? One nice way to check if they're equal is to see if they agree on a basis, right? To multiply a basis on the left by each one of these matrices and see what you get as a result. All right, well, let's, well, we have a handy basis, right? We have this basis of eigenvectors. So for A, what happens to these eigenvectors if we multiply on the left by A? Well, we get the corresponding eigenvalue times that eigenvector, right? This is just because we assumed these are eigenvectors. Now let's see what happens if we multiply VI on the left by B. Well, B is P times D times P inverse, okay, times VI. What is P inverse times VI? Well, P times EI is VI, and that means that P inverse times VI is EI. So this is P times D times EI. What is D times EI? Well, EI just picks off the ith diagonal entry here. So P times lambda I times EI. Now we can move the lambda I times P times EI. And P times EI, that's VI. So this is lambda I VI. So you can see that what multiplication by A does to this basis is the same as what multiplication by B does to this basis. And that means that A is actually equal to B, but B was P, D, P inverse. So, so that means that A is diagonalizable. So this gives us an if and only if condition for diagonalizability. A matrix is diagonalizable if and only if there's some basis for Rn consisting entirely of eigenvectors for A. So this is the sense in which diagonal matrices are sort of the only nice linear transformations in the sense that I meant at the beginning. There are other matrices that are not diagonal that act just by stretching a basis, but all of those matrices are diagonalizable, right? If a matrix acts just by stretching some basis by different amounts, each of those basis vectors are actually eigenvalues for the matrix, or eigenvectors for the matrix, and the matrix for the linear transformation relative to that basis will be diagonal.